What specific problem does your proposed method aim to solve in relation to hallucinations in large language models, and why is it significant for applications like healthcare?
The proposed method aims to address the issue of hallucinations in large language models, LLMs, by uncovering and utilizing entity recognition directions that help the model assess its own knowledge about specific entities. This is significant because hallucinations, where the model generates fluent but factually incorrect information, pose a critical risk in applications like healthcare, where accuracy is paramount. By operationalizing the phenomenon of knowledge refusal and identifying linear directions in the representation space that indicate self-knowledge, the method allows for better control over when the model should refuse to answer versus when it might hallucinate. This understanding not only enhances the reliability of LLMs in sensitive domains, but also contributes to a mechanistic interpretation of how these models can be fine-tuned to minimize the risk of generating misleading information. Ultimately, the findings suggest that steering the model using these entity recognition directions can significantly reduce the likelihood of hallucinations, thereby improving the factuality of responses in high-stakes environments.
Can you provide a step-by-step explanation of how your proposed method works, specifically detailing the role of sparse autoencoders in identifying self-knowledge directions in the model's representation space?
Our proposed method utilizes sparse autoencoders, SAEs, to identify self-knowledge directions in the model's representation space through a systematic approach. First, we train SAEs on the internal representations of the Gemma 2 models, which allows us to project these representations into a higher dimensional space while enforcing sparsity, enhancing interpretability. Next, we analyze the activations of the SAEs across different layers, focusing on the final token of entities to detect whether the model can recall facts about them. We compute separation scores to distinguish between known and unknown entities, revealing that certain latent directions are highly effective in differentiating these categories. Finally, we demonstrate that these identified directions causally influence the model's knowledge refusal behavior, indicating that they encode a form of self-knowledge regarding the model's capabilities to recall factual information about specific entities.
Could you illustrate your proposed algorithm using a specific example of a known and an unknown entity, walking through the steps of how the model's response is influenced by the entity recognition latents?
To illustrate the proposed algorithm, consider the known entity LeBron James, a basketball player, and the unknown entity Wilson Brown, a non-existent player. First, we prompt the model with a question about the known entity, such as, "What team does LeBron James play for?" The model activates the entity recognition latents associated with known entities, which enhances its attention to the last token and allows it to accurately recall relevant attributes, resulting in a correct response. Conversely, when prompted with "What team does Wilson Brown play for?" the model recognizes Wilson Brown as an unknown entity. The activation of the unknown entity latents suppresses attention to the last token, leading the model to refuse to answer or hallucinate a response. This demonstrates how steering with entity recognition latents can directly influence the model's ability to recall factual information or induce knowledge refusal based on the entity's recognition status.
What are the primary theoretical or practical benefits of your method compared to existing approaches in mitigating hallucinations in LLMs, especially in terms of accuracy and generalizability?
The primary theoretical benefit of our method lies in the discovery of entity recognition directions within the representation space of large language models, LLMs, which allows for a nuanced understanding of how these models assess their own knowledge. By utilizing sparse autoencoders, SAEs, we can identify specific latent directions that causally affect knowledge refusal and hallucination behaviors, providing a mechanistic insight that existing approaches lack. Practically, our method demonstrates improved accuracy by steering the model's responses based on its self-knowledge, enabling it to refuse to answer questions about unknown entities rather than generating incorrect information. Furthermore, The entity recognition directions we identified generalize across various entity types, such as players, movies, and cities, indicating a robust capability to handle diverse queries. This generalizability enhances the model's reliability in real-world applications, particularly in critical domains like healthcare, where factual accuracy is paramount.
How did you validate the effectiveness of your method, and what experimental designs or metrics did you utilize to demonstrate its impact on knowledge refusal and hallucination rates?
To validate the effectiveness of our method, we conducted experiments using a test set of 100 questions about unknown entities, measuring the model's refusal rates by steering with entity recognition latents. We observed that increasing the activation of known entity latents reduced refusal rates across 3 entity types, while increasing unknown entity latents induced nearly 100% refusal. Additionally, we compared the performance of our model against an orthogonalized baseline, which showed a significant reduction in refusal responses, indicating the crucial role of the entity recognition direction in knowledge refusal behavior. We also analyzed the attention scores of the model, revealing that steering with known entity latents increased attention to relevant tokens, while steering with unknown latents decreased attention, further demonstrating the impact of our method on the model's factual recall mechanism. Lastly, we quantified the differences in activation levels between correct and incorrect responses using t-statistics, achieving a 73 to a UROC score, which underscores the effectiveness of our approach in distinguishing between accurate and erroneous outputs.
What limitations or potential drawbacks did you encounter with your approach, and how might these inform future research or applications in the field of mechanistic interpretability in LLMs?
One limitation encountered in our approach is the specificity of the entity recognition directions, which may not generalize well across all types of entities or contexts, as indicated by the varying effectiveness of the say latents in different layers of the model. Additionally, while we found that steering with these latents can influence knowledge refusal and hallucination behavior, the effects were less pronounced in the GEMMA 2.9b model compared to the 2b model, suggesting that model architecture may impact the efficacy of our method. Furthermore, our reliance on fuzzy string matching to measure correctness could introduce inaccuracies, particularly in distinguishing between closely related attributes. These limitations highlight the need for further exploration into the hierarchical organization of entity representations and the development of more robust evaluation metrics. Future research could focus on enhancing the generalizability of entity recognition latents and investigating alternative methods for assessing model uncertainty and factual accuracy.